Hello, everyone, and thank you so much for joining the first TelcoForge webinar. Certainly not the last, if I have anything to do with it. My name's Alex Lawrence, and I'll be the moderator for today. TelcoForge aims to be a community for building a better telecoms industry, and that community piece is important. So if you see an issue which needs addressing or a problem which just isn't getting dealt with, we're here to raise awareness about it and really help solve that problem. And so your input is important. I mean, during this webinar, of course, but generally as well, because if we want to see major changes in the industry, it means solving the thousands of small problems that we face day to day. So on with the webinar. Having said that, I'm fortunate enough to be joined by Andreas Roessler and Francesco Rossetto from Rohde Schwarz. They've been working on making some of the concepts in 5G Advanced a reality, not least what's being termed an AI native air interface. Now, today they're going to share some of the details of that work, particularly on one use case for channel state information feedback, as an indicator for what we might see to come in next generation networks. Now, Andreas and Francesco are live here today, but for the first part of this webinar, because it's quite a technically complex subject, which requires a level of precision in the language, Andreas has recorded an initial video presentation, so I'll play that to get us all up to speed. But send in your questions as they occur to you, because either we'll talk about them later on, or the fellows might be open to typing some answers as we're going through the video as well. So you've got that opportunity to take advantage of. Now, please note that we will have a recording of the webinar available in around 24 hours from now on the TelcoForge site. So if you miss something or you need to revisit any issues, or even flag up a topic to a colleague, then it should be fairly easily locatable. For now, though, let me hand over to the virtual Andreas.
The evolution of wireless communication continues to push the boundaries of innovation, particularly with the advent of 5G Advanced and the foundation of an AI-native air interface in a future 6G standard. Today, we will examine machine learning-based enhancements for channel state information feedback in 5G Advanced, as currently studied and standardized in 3GPP releases 18 and 19. We will explore how AI and ML are used to optimize CSI feedback, reducing overhead and improving performance. This topic is significant as it defines a baseline and therefore contributes to the developing of an AI-native air interface for a future 6G standard. So as an agenda for today, I brought you the following topics. So we will review the air interface use cases in 3GPP releases 18 and 19 that are AI/ML related. I will explore with you how CSIRS and the feedback and reporting is defined in the current 5G new radio standard. We will discuss why machine learning-based CSI feedback enhancements in 5G Advanced are relevant. And then, of course, look at what role test and measurement plays. So let's get started. AI/ML is, of course, not unknown to 3GPP. Until now, the main driver in previous releases was the core network, using it for data collection and data analytics. The how is typically left up for implementation, but explicitly mentions the use of AI/ML-based methods. An essential first step was the addition of the network data analytics function with 3GPP release 15. The NWDAF is a key part of the 5G core network, offering analysis of network slices that greatly improves operational intelligence across network functions. The NWAF was further developed in 3GPP release 17, where it gained two new logical entities: the analytics logical function and the model training logical function. The MTLF is responsible for creating and improving machine learning models and supporting the launch of new training services that enhance the network's adaptability. Meanwhile, the ANLF focuses on conducting detailed inference analysis and data analytics, improving network reliability and performance. Also in FreeGPP Release 17, the RAN3 working group led the first study on an AI-enabled radio access network. This study identified high-level principles for defining the functional framework using machine learning by investigating some example use cases such as network energy saving, load balancing, and mobility optimization. FreeGPP Release 18 marks the beginning of 5G Advanced, which includes many new AI/ML related study items led by various technical specification groups within the standardization body. The System and Service Aspect Working Group 1, SA1, explores methods for sharing AI/ML models across the 5G network, paving the way for a more interconnected and intelligent network fabric. At the same time, the SAA2 group looks at the architectural support of AI/ML-based services within the 5G system, laying the foundation and improved service delivery and operational efficiency. The SA4 group, which focuses on media services, examines potential use cases of AI/ML for 5G media codecs, offering significant improvements in media quality and delivery. Meanwhile, SAI5 tackles the important issue of AI/ML management, aiming to harmonize AI/ML functions across 5G systems for easier management, orchestration, and charging. Regarding the radio access network, there are also two studies in Release 18. First, as a continuation of the earlier mentioned Release 17 study item, RAN3 conducts normative work to specify enhancements for data collection and signaling support for energy saving, load balancing, and mobility optimization. Second, the most significant study item is the one covered in Technical Report 38483 on AI/ML for the NR air interface. Many researchers of academic institutions and key industry players believe that 6G will natively support AI/ML for the air interface. Therefore, an initial study from a 5G perspective to define general framework for augmenting air interface functionality to support AI/ML-based algorithms with the goal to enhance performance and reduce complexity and overhead seems evident. To achieve this, FreeGPP has agreed to study 3 pilot use cases. So first, CSIRS feedback enhancement, which focuses on improving the feedback mechanism by estimating the mobile radio channel using channel state information reference signals and reporting the channel state information back to the base station. The goal is to use AI/ML techniques and compress the channel state information to reduce redundancy and therefore enable compression. This mechanism is combined with AI/ML-based prediction of the mobile radio channel's evolution, aiming to increase the interval, less frequent transmission of the channel state information feedback in the uplink direction. So the use case is split into 2 sub-use cases, compression and prediction. The second scenario explores the use of AI/ML to reduce beamforming management overhead and improve beam selection accuracy through spatial and temporal prediction. This could significantly benefit energy consumption and battery life at the UE site. The third scenario aims to improve positioning estimation accuracy using AI/ML-based techniques, especially in heavy non-line of sight conditions, such as in industrial environments, for example, a factory hall. 2 aspects were investigated. First, a trained AI/ML model is used to directly infer the UE's position, known as fingerprinting. The second aspect is AI/ML-based assisted positioning, where the AI/ML model inference output enhances on existing measurements, such as providing a non-line of sight indicator. All these 3 initial use cases present very interesting scenarios to define a general framework for AI/ML usage for the air interface. However, the CSI feedback enhancement is particularly interesting from a test measurement perspective. That interest is driven by the compression aspect, which requires tight interplay between the base station, the G-Node B, and the mobile device, the UE, as the encoder is running on the device, where the decoder resides in the network. Due to the individual complexity, there's a different level of progress for studying these three initial use cases. Beam management, position accuracy enhancement, and the prediction component have reached a state where these study items were transferred into work item state and therefore become officially part of 3GPP Release 19. The functional freeze for Release 19 is planned for September 2025, with a subsequent ASN1 freeze at the end of 2025. The compression part for the CSI feedback enhancement remains a study item. The 3GPP delegates agreed that additional time is required throughout the definition of Release 19 to thoroughly analyze the impact on specifications and define an adequate framework. And for completing the picture of the current general status within specifications, a new use case was added in Release 19 to study AI/ML-based enhancements for mobility in the 5G new radio standard. Before we now continue to look a bit more in detail into the aspects of machine learning-based CSI feedback enhancement, it is worthwhile to recap the fundamentals of CSIRS in the 5G new radio standard. Of course, we can give here only a brief overview and summary. Therefore, I would like to point all of you to the well-known Rohde Schwarz 5G new radio ebook for relevant details on the set of reference signals defined for 5G. With the definition of 5G, the standardization experts replaced the one-fits-all approach with a more specific approach in terms of reference signals to address issues discovered in 4G LTE, which included overcome limitations in terms of flexible network deployments, address energy efficiency aspects due to the always-on nature of reference signals in LTE, especially in downlink direction. Their non-applicability for frequencies beyond 6 GHz, in particularly for FR2 millimeter wave, and their non-friendliness while working with a larger number of antenna elements and therefore antenna ports. The result is a set of reference signals in downlink and uplink direction tailored for specific tasks, which can be flexibly adapted for different deployment scenarios and spectrum usage, where the configuration can also be specific per device. However, also several devices can receive the same configuration. This is particularly important for the so-called channel state information reference signals, CSIRS, that are used for determining the received signal quality in downlink direction and used for several different purposes. There are three main categories for CSIRS signals. Non-zero power CSIRS, where those signals can be used for channel measurements and consequent reporting of channel state information, or they are used for intra-cell interference measurements. Then there are non-zero power CSIRS that are configured for inter-cell interference measurements. For these three categories of CSIRS signals, the corresponding information on how these signals are parameterized is signaled to the UE with a specific layer 3 RRC signaling message as part of the CSI measurement configuration message. Last but not least, and aiming for the complete picture, we have zero power CSIRS configured by the means of the PDSCH configuration message, which we won't discuss further here. Non-zero power CSIRS are used for several procedures where some of the listed functions can also be completed using synchronization signal blocks measurements. For example, connected mode mobility, radio link failure detection, and beam failure detection. For the remainder of this webinar, we will solely discuss the use of channel measurements and channel reporting. To do the measurements, the UE needs to know where to find the resource elements carrying CSIRS in the time frequency grid and what initialization is used to generate the respective sequence that is mapped to these resources. As shown, a pseudo-random sequence RM is used, which is initialized with CINIT at the start of each of the M symbol L, depending on the slot number within the radio frame, multiplied with a specific scrambling ID, where higher layers provide this information to the UE. The PN sequence is multiplied with a power offset, set in relation to resource elements carrying the secondary synchronization signal. So the CSIRS power is relative to the power used for the secondary synchronization signal, and either half of it, same, doubled, or quadrupled. The sequence is further multiplied with weighting factors depending on the CDM type determined by parameters K' and L'. The higher layer CSIRS resource mapping information element defines the CDM type. The CDM type, or code division multiplexing type in 5G New Radio, defines how CSIRS antenna ports are grouped and mapped onto physical resource elements in both time and frequency domain. It determines how resources are shared among different antenna ports and the degree of separation between signals transmitted on these ports, achieved through orthogonal or quasi-orthogonal spreading. This grouping has a direct impact on critical aspects of network performance. First, it plays a key role in interference management, where better separation enhances signal clarity. Second, it ensures feedback accuracy, as proper grouping allows for a more precise estimation of channel state information, which is essential for optimizing network operations. This sequence is now mapped to a frequency and time resource K and L, where K represents the subcarrier and L, as already mentioned, the OFDM symbol in the resource grid. The sparsity in frequency and time domain, for instance, if two consecutive subcarriers or OFDM symbols are occupied, is defined through parameters K bar and L bar and K prime and L prime. If these parameters are present depends on the provided CSIRS resource configuration given by the here mentioned table in the 3GPP specification. Further, the mapping is dependent on the density in the frequency domain defined for an antenna port ρ. CSIRS signals can use up to 32 antenna ports, as you can see here. And here we see now the various configuration possibilities for CSIRS and subsequently the number of antenna ports, the density and occupation of subcarriers and symbols in a time frequency grid. Let's take an example with row 8. As you can see, L' is set to 0 and 1, and we have the OFDM symbol L0. Then we also see K' can take the values 0 and 1, and we need to understand where we also find the information on what K0 and K1 is. So the real question is, where does the UE know these parameters from? And of course, that's a complex process that is based on signaling procedures, but the determination of CSIRS resources follows a stepwise approach governed by the three key 3GPP technical specification 38211, which defines physical signals and modulation, 38214, which details physical layer procedures, and 38331, which addresses the higher signaling portion. The mapping of the CSIRS sequence in the time frequency grid is specified by the CSIRS resource mapping information element. In the example from the previous slide, we have 8 antenna ports, a density of 1, and a CDM type of CDM4 FD2 TD2. Based on this configuration, the UE refers to the corresponding row in the table defined in 38211, and for row 8, the values for K' and L' are determined to be 0 and 1 respectively. The specific OFDM symbol carrying the CSIRS is also part of the CSIRS resource mapping configuration. Let's assume it is set to the 12th OFDM symbol in one slot. Since L' is configured as 0 and 1 as per row 8, the CSIRS signals will occupy both the 12th and the 13th OFDM symbol. Now, considering the frequency domain allocation for row 8, the allocation type is others, with a total of 6 bits. For example, if the bitmap is 110000, according to 38211, the interpretation of the bitmap is that f of I represents the eth bit number of each bit that is set to 1 in this particular bitmap I mentioned. This repeats across every resource block configuration for CSIRS reception, where the example based on row 8 is the density of 1, indicating the allocation applies to every resource block in the signal bandwidth. But what does that mean? For the bitmap 110000, the 5th and the 4th bits are set to 1, so that's B5 and B4. Multiplying these indices by 2 yields subcarriers 8 and 10 within a resource block, will carrying the CSIRS reference signal in the frequency domain. And again, since K prime values are set to 0 and 1, the consecutive subcarriers 9 and 11 are also occupied. Therefore, within each resource block, subcarriers 8 to 11 are used over 2 OFDM symbols, 12 and 13, for CSIRS. Lastly, the resource block allocation within the signal bandwidth is configured. The minimum allocation is 24 PRBs, incremented in steps of 4, as defined by the higher layer signaling. I know this is quite a bit of information to digest. So here's a visual representation of what I just explained. You see the resources occupied by CSIRS based on the configuration on the left. This configuration is actually from a live 5G network operated by a US service provider, collected with one of the latest 5G smartphones and the Rohde Schwarz Qualipoc Android, our premium handheld mobile network troubleshooter. Next is the mentioned scrambling ID used for the initialization sequence we discussed a couple of minutes ago. And last, the periodicity configuration means how often CSIRS transmitted from a timing perspective. In the example log, it's 320 slots with an offset of 60. And obviously there's not only one configuration, there are multiple for one service provider. For example, when using another infrastructure provider for his 5G network within another geographical area, which is typically the case in the United States. However, the second log here is with the same device type, but for a different operator. As you can see from the configuration, quite a different setup with an increased number of antenna ports, 2 symbol allocation, means L0 and L1 are configured, and a denser mapping per resource block in the frequency domain required due to the increased number of antenna ports. So not just frequency allocation differs, but also the periodicity. In this example, it is set to 40 slots and 8 slots offset. So the slot duration is subcarrier spacing dependent and defined as 1 over 2 times the subcarrier spacing. So with the network operating at FR1 frequency and subcarrier spacing of 30 kHz, the 40 slots correspond to a duration of 20 milliseconds. With the offset of 8, it simply means that the CSIRS configuration is transmitted in slot 8, 48, 88, and so forth, which is determined by the shown equation. The user equipment now performs several key measurements on the CSIRS to assess the quality of the downlink channel. These measurements serve as the basis for computing additional parameters. The process starts by measuring CSIRS reference signal receive power, which reflects the average power received from the CSIRS resource elements. This measurement provides a critical understanding of the signal strength, aiding the mobility management and beam evaluation. Next is CSIRS-RQ, or reference signal received quality, where this metric, which is the ratio of CSIRS-RP to the reference signal received strength indicator, which helps to evaluate the signal's quality relative to interference and noise. And then there's SINR, or signal to interference plus noise ratio. This measurement accounts for the interference from other cells and background noise, providing a comprehensive assessment of the channel signal quality, which is crucial for link adaptation and throughput optimization. Based on these physical layer measurements, additional parameters are computed, among them CQI, PMI, and RI. The CQI, the channel quality indicator, indicates the highest modulation encoding scheme that the channel can support. The pre-coding matrix indicator suggests the optimal pre-coding matrix for data transmission and the rank indicator denotes the number of special layers the channel can support. Based on these measurements and the reported information, the G-Node B can, for example, select a precoding matrix to beamform the transmission of the data channel and its demodulation reference signals and adapt it to the actual channel conditions as seen by the device. There are dependencies on how these parameters are calculated, which are listed in this table according to the specification 38214. However, this is only the tip of the iceberg, as the reporting of CSI is one of the most complicated aspects in the entire 5G new radio specification. So this table here summarizes the evolution of codebooks, so the use of precoding metrics, across the different releases of the 5G new radio standard. Of course, we don't have the time here to focus on all details. Therefore, I would like to refer you to the mentioned paper, which gives an excellent overview on the different codebooks, starting with Type 1 codebook. Defined in Release 15, it focuses on single beam feedback, suitable for line-of-sight scenarios, focusing on different antenna types. Type 2 codebook, also introduced in Release 15, extends the feedback by supporting multiple beams, addressing multipath environments common in a multi-user MIMO environment. In Release 16, the enhanced Type 2 codebook incorporated spatial and frequency domain compression using DFT and IDFT techniques, reducing feedback overhead while maintaining high spectral efficiency. The evolution continued in Release 17 with port selection codebooks leveraging partial channel reciprocity for massive MIMO. And why does that matter in this context? Well, it explains why we intend to use AI and machine learning for CSI feedback enhancement. The progression towards massive MIMO in 5G and predicted ultra-massive MIMO in a future 6G standard has amplified feedback overhead, making traditional methods less feasible. Let's get into the weeds, shall we? In enhanced Type 2 codebook feedback defined in Release 16, the UE estimates the downlink channel and reports a quantized approximation of the CSI to the G-Node B. The calculations I show here is a simplified example demonstrating the general concept, and I omit some of the details as it would take too much time to explain them. However, if we check technical specification 38212 and the mentioned table, we find the information on calculating the PMI feedback bit width for the enhanced Type 2 codebook for different transmission modes. I show rank 1 as an example here, but the table contains way more information. N1, N2 are set and signaled to the UE by higher layer parameters. If we assume we have 32 antenna ports to report, like in one of our previous examples, then we have different settings for N1, N2, O1 and O2. Oversampling factors, in the example both set to 4, were defined to create a larger virtual grid for a finer beam selection by the UE instead of just relying on the discrete physical antenna array configuration. Also, the number of beams L is signaled to the UE and is based on a so-called parameter combination. With these parameters, we calculate the horizontal and vertical beam feedback, the spatial compression, amplitude feedback, and phase feedback. So here I give you two examples without showing the entire calculation. For example, if we assume the 32 antenna ports, the rank 1, where I show all these 3 different tables, dividing the signal bandwidth and reporting into 18 subbands where we're sending reports to, the number of beams L is set to 6. The PMI feedback bit width is 287 bits that we have to send back to the network for channel state information feedback. If we just take example 2 here, same number of antenna ports, but rank 2 transmission, so 2 layers, 18 subbands, same number of beams, you see how this number not just doubles because the wideband feedback is always the same number, but it is 479 bits. And then if we drop down a little bit in the number of beams that's being used, L4, you see it's 307 bits. So as you can see here, this is quite some overhead. Yeah? And therefore, the idea is now to use AI/ML to compress this feedback and send it back to the network. The question is, how are we going to do that? And the answer is based on using an autoencoder. So an autoencoder is a particular type of machine learning model consisting of an encoder and a decoder. I mentioned that words already a couple of times, that now learns efficient data coding in an unsupervised manner. In the shown example, I have a waveform represented by its IQ samples, and I use an autoencoder to compress this information, transmit then only the latent space information, and the decoder will reconstruct the original data at a minimum level of distortion. The reconstruction accuracy is typically given by the normalized mean square error or as a squared generalized cosine similarity. In the context of CSI feedback, the encoder compresses high-dimensional input data, such as CSI matrices, into a lower dimensional representation, while the decoder reconstructs the original data from the compressed one. Using autoencoders significantly reduces feedback overhead by lowering the number of bits required to convey channel information. Despite this compression, autoencoders preserve high reconstruction accuracy, ensuring the base station receives precise and reliable channel state information. When designing and training these models, they shall adapt well to varying channel conditions, making them suitable for dense dynamic network environments. And furthermore, autoencoders are scalable, enabling efficient operations in systems with large antenna arrays, where traditional feedback methods struggle due to the high dimensionality of the CSI. So now the figure on the left shows 3 representative frameworks for machine learning-based CSI feedback. Option A is a one-sided refinement for implicit CSI feedback. Option B, a two-sided enhancement for implicit channel state information feedback. And option C, a two-sided enhancement for explicit CSI feedback. In the case of explicit mechanism, the complete channel matrix is sent back to the base station. The implicit mechanism, on the other hand, sends a more compact version of the channel matrix back to the network. This version is in the form of eigenvectors. Compared to the codebook from release 15 and 16, the only change in implicit feedback is the PMI definition. Instead of using the traditional codebook, AI-compressed pre-coding vectors are transmitted. Most vendors prioritize implicit feedback when establishing their AI framework to enable backward compatibility with the legacy codebook-based approach. That means that the UE obtains an eigenvector V from a raw channel matrix H, encodes V using the encoder to a feedback bitstream S, and forwards this information to the base station. The base station could decode the received bitstream S to V prime through the decoder and recover the pre-extracted CSI information. Here's now a specific autoencoder architecture called BIM-CSI-NET, where the eigenvector extracted from the full channel matrix serves as an input to the encoder. The encoder itself uses now 3 so-called long short-term memory layers to learn and extract the correlation between the different subbands and therefore reduce the overhead while maintaining reconstruction accuracy. As we can see from the table, when comparing the number of type 2 codebook feedback bits and achievable reconstruction accuracy, we see that with the autoencoder approach, the number of feedback bits is almost cut in half while maintaining the same accuracy. So I hope you are not too confused after all this theory, but it is necessary to understand what happens next. And next is a demonstration by my colleague Francesco Rossetto to show you how you can test for all these different complex features and functionality. Francesco, floor is yours.
Hello everybody, and thank you for joining our webinar. My name is Francesco Rossetto, and today I will talk about how AI/ML can improve a fundamental part of a cellular system, CSI reporting. Before going into the live part, let us provide a few important background details. In the CSI report compression setting, a UE transmits a compressed CSI report to a base station. When AI/ML compression comes into play, both the UE and the base station include a beamformer, compressor, and decompressor, respectively. We at Rohde Schwarz want to early investigate this exciting feature where AI is deployed also at the base station side. In this sense, two aspects are needed. On the one hand, our base station emulator, the CMX500, must be able to run in real time a neural network, and on the other hand, a UE capable of CSI compression is required. Since this feature is not yet officially standardized in 5G and no commercial UE supports it, our R&D labs have replaced the UE side with an appropriate UE MOX that can support the AI ML CSI compression. In a first approach, our R&D labs have used a software-defined non-real-time UE named MATLAB UE. In this setting, the UE is configured with a valid S1 configuration for CSI reporting and replaces the conventional CSI bits with those generated from the neural encoder. We remark that this approach tries to be minimally invasive of the 5G standard, since the existing format of CSI transmission is not changed. For instance, the CSI bits are transmitted on the uplink as expected in a conventional CSI report. Just the length and the interpretation of the CSI bit string is different than usual. We have implemented this approach in the CMX500 and in our in-house software-defined UE, and recorded a video with an execution of this scenario. Let us go through it. You can see a representation of the setup with the CMX500 connected to the MATLAB UE. Let us remark that the CMX500 has been extended so as to be able to load a user-defined neural network decompressor. We will first spend a few words on the used neural network architecture, which is in IM-CSI-NET. This network is based on dense layers, whose inputs are the subband beamformers stacked on top of each other. This concatenation generates a single numerical vector passed as input to the network. The output of the encoder is then quantized by a scalar quantizer into a bit string, which is then transmitted by the MATLAB UE. The CMX recovers the CSI bits and passes them into the neural decoder and reconstructs the beamformer. The top right tile on the screen shows a comparison of the reconstruction quality between the neural network, the blue line, and the 3GPP E-type 2 baseline, green crosses. As you can see, the AI-based compression can significantly reduce the number of necessary CSI bits for the same reconstruction quality compared to the state-of-the-art CSI reporting from 3GPP. You may wonder which scenario we are discussing. We simulate a random drop of the UE in an urban environment and generate the fading channel correspondingly. As time progresses, the MATLAB UE computes new reports and the CMX500 decompresses them. In this environment, we can replay the same set of channels, and therefore we can compute the reconstruction accuracy for both the neural network-based compression and the 3GPP E-type 2 baseline. The AI-based approach is mostly superior to the 3GPP baseline in spite of the much smaller reporter size. An alternative to test this AI signal processing is to replace the UE with a 5G signal generator, the Rohde Schwarz SMW200. The SMW200 can generate 5G uplink signals, and in this setting, the SMW200 sends a modified uplink signaling packet on push. More specifically, the SMW200 generates a so-called uplink MEC-CE. By other words, an uplink signaling packet at MEC level, and the special thing about this packet is that it includes the compressed CSI report as well as much debugging information. This approach is not really spec compliant, since no CSI report is normally transmitted on an uplink MEC-CE. but the additional information greatly helps to debug this feature. The CMX500 continues to work as the base station emulator and processes the uplink packets. Let us have a look at the devices and at the demo. The CMX500 can be controlled by means of a Python-based scripting language called XLAPI. And here is a very simple example scenario. Let us stress that in this scenario, we can name a neural network decoder that will be uploaded to our device. You can also see in this script that the file with the MaxCEs for the signal generator can be defined. So effectively, both sides are now tuned for execution. We mentioned that we want to transmit a user-defined, non-spec compliant set of MaxCEs, and this set of MaxCEs can be set in the Python-based scenario. Let us have a quick look at this file in the SMW200. In order to do so, we open up the 5G configuration, go to scheduling, select the subframe where we want to transmit the uplink MaxCE, and then go into the user settings. Under properties, then we can name a text file which includes the user-defined payload. We then go to the CMX500, our base station emulator. For the sake of brevity, we show a message log at the end of the scenario. Let us then open such a file and show the two key messages from a log. First, let us have a look at the SE1 configuration. You can notice the CSI reporting. Right at the end, we see that we can name a neural network that can be configured in the CMX500. Moreover, we mentioned that the CMX500 is able to receive the UE uplink, decompress the information from the UE, and display it for further evaluation. Indeed, in this message, you can see both the output of the neural decoder and the computed beamformers for the downlink. That was all from my side for today. I hope we could show the ability of the Rohde Schwarz devices in early testing of AI algorithms for 3GPP. And now back to you, Andreas. Thank you for letting me show this demo.
So here are your key takeaways from today's webinar. So 3GPP currently lays the foundation for an AI native air interface in a future 6G standard by studying 3 pilot use cases in 3GPP releases 18 and 19 as part of 5G Advanced. 2 of the 3 pilot use cases, so to name beam management and positioning, were already transferred to the work item stage in release 19. CSI feedback enhancements use case, the compression part remains a study item. Prediction has moved into the work item stage. And with release 19, we also have a new use case that is being studied, which is mobility. CSI feedback enhancements, the compression aspect is based on a 2-sided model, which makes it challenging and complex, and that's why it needs more time. 2-sided means the UE hosts the encoder, the G-Node B hosts the decoder, as we explained and also have seen in the demo. And from a test and measurement point of view, we will help to ensure the interoperability between models, for instance, designed by different vendors, help with the model transfer, and of course to confirm the expected performance gains before any of these concepts are deployed. I know this was a lot of information to digest, no doubt about that, but I hope it helps you to understand why machine learning based CSI enhanced feedback is so important and add value towards the specification, will help us to manage the integration of AI ML into 5G and use that information, of course, then to define a future 6G standard. With that, thanks for your attention, and we see you next time.
Well, that was really interesting, and thank you, Francesco and Andreas, for that. And thank you in the audience for your questions so far. I'm really keen to encourage any of you to send in further thoughts or questions in the time that we have remaining. I did have a question though. You mentioned the interaction between the user's device and the network, but how can you guarantee that they're using the same model, particularly if you're coming from let's say roaming from even a different country or something like that? Is there a way to make sure that the device and the base station can be compatible, sort of almost regardless of?
Alex, maybe I take a first step at this question, and then Francesco can chime in and correct me if I just say something stupid. But what will happen in the initial phase, from our point of view, is that there will be the models will be trained offline, right? So that might be that an infrastructure vendor and a device or a chipset vendor work together, deciding on an architecture. They can decide on different architectures, right, for different deployment scenarios, for instance. And then 3GPP is working right now on procedures to basically instruct the mobile device which of the models to use under certain circumstances, right? So we have implemented or suggested model IDs that point to these different models. And then through a signaling procedure, basically the base station, the network can dictate or suggest to the UE to use this particular model for the compression of the CSI measurements. I think that's a straight way forward. I think there's a lot of room also to improvements, right? So for instance, how we get these models pre-installed on the devices, how we get them updated. All this is currently being discussed in 3GPP. And I don't know, maybe Francesco has a few thoughts on that as well.
Yes, so as of now, there is, so 3GPP has not really defined how the base station and the UE should be tuned in this respect. So the current discussion goes possibly in two directions. Both of them have pros and cons. One direction is that if we have a physical UE that then goes into a mobile cell, the base station may effectively push the specific encoder for its own cell into the UE. So that defines per definition or that the two sides are tuned to each other. Of course, that may not be desirable by everyone, especially by the UE vendors, because they receive some files, some model, and they have no idea what may be inside it. And that, for instance, they don't know whether it's tuned to their hardware or they don't know whether it's really a model or not something else. So there are open topics. Another possibility is that the 3GPP may define a set of scenarios, something like rural or downtown street canyons and so on. And therefore, each vendor, so both base station and UE, may define their own encoders and decoders for those scenarios. 3GPP may also provide certain data sets for each scenario. And therefore, then the base station will announce in its S1 configuration which of these scenarios should be applied. So the UE will then possibly have this firmware either on premises or it may be taken from a safe server, whose information is then trusted. So these are currently the two major versions that we could experience so far.
Brilliant, thank you. I mean, there's plenty there to jump into more deeply, but I'd like to sort of highlight one of the questions from the audience, which has come in without a name, but it's suggesting that maybe the autoencoder approach might be quite simple, and is a GAN based network an alternative answer? Now, I don't know if that's something that you've looked at, or I guess maybe the question really is why use an autoencoder rather than another solution?
Well, maybe I can take it on it, Andreas. So I simply think that the autoencoder is relatively well-known structure that can find a compressed version or representation of data. It also has a visibility that it can be split into two parts, an encoder for the UE and a decoder for the base station. So, and also maybe let me remark, this is report compression has its benefits for the performance of the mobile network. It's, however, also regarded as a kind of stepping stone for 3GPP into this kind of artificial intelligence signal processing. So 3GPP is also not excluding to use other architectures. So there could be also a transform-based architecture and so on and so forth. There are discussions in this direction. So what the question has, its I would say correctness. GAN itself, as far as I know, has not been investigated by 3GPP. I cannot specifically name a reason for that, but I believe that 3GPP is currently just trying to get something working effectively. And then possibility to extend with more advanced networks is welcome. I don't think it's their current focus. 3GPP is just trying to get the signaling right so that both sides are all tuned to each other.
Yeah. So maybe to add to that, because I think Francesco mentions very, very relevant and important points here that we shouldn't forget, right? The goal right now with release 18 and 19, and then probably continuing release 20, is to establish AI ML framework in 3GPP that we basically can then use as a foundation while we're moving forward into 6G standardization with release 21, as it was outlined by 3GPP already. So that means we need to start with something that is understood, well understood, right? And like Francesco mentioned, autoencoders are around for a long time. They're used for compression for a long time. The concepts are understood. And now we're taking this understood concept of CNNs with dense layers and all that stuff and apply it to our field of wireless communication. So that means we trying to make a complex task by itself or manageable, right? So if you currently look into academics and research, there is work going on transformers already, right? So what is important to understand is that in the future, I think 3GPP will make sure that new architectures or other architectures are not excluded, as also mentioned by Francesco. And this is also the reason why we here at Rohde Schwarz implemented the ONNX interface on our CMX500 platform, because that allows the integration of model architectures into our platform. Now, the only question is, of course, like how complex those such models are and can they be executed in real time? And I think that's also something that 3GPP still is investigating today, because, we can talk architectures, autoencoder, transformers, variational autoencoder, whatever. But if we define architectures that then are not executable, but they work great in simulation, they're not executable in real time on real hardware, on real future chipsets, on base stations, and such, then we have done something wrong, right? So there's always also like I don't want to call it a setback, but something that needs to be considered while also looking into new architectures and new approaches to this. But hey, we all have a few more years till retirement, right? We shouldn't solve all the problems with 6G or 5G advanced right away. Let's leave something for 7G, 7.5G, 8G. If, personally, I plan to retire in 13 years or 20 years, something like that, right? So there is something to do for us here in the future as well. So I didn't want to make it a joke, but I think that's hopefully giving some insights of what's going on, what the initial steps look like, and how this might evolve in the future then towards a 6G standard. So back to you, Alex.
Yeah, there is a related question, I suppose, which is to do with the resources available at the base station and or on the device, because I know that telcos are under quite a lot of pressure to be sort of reducing power consumption, and AI can be pretty energy and processing intensive. So to what extent are you sort of using these models now, because they fit the resource constraints at the base station? Are they much more complex or more resource heavy than sort of previous CSI computation algorithms and that kind of thing?
Indeed, a very good question. Let me add a few thoughts, and then Francesco from the implementation side can hopefully share his opinion as well. I mean, like for GBP, we didn't want to start with the most complex architecture, with the most parameters and such, and just break the system, right? So we also did a literature study. We looked into what's already around there, and what is as close as possible as 3GPP is operating today, right? And that resulted in a model that Francesco described during his presentation and demonstration, and that helped us to just like execute in the hardware framework that we have available right now. However, of course, we need to follow what's being discussed in 3GPP. I think, like, for those in the audience that are experts or have experts in their company contributing to this discussion, they all know that right now the reference autoencoder that's being used and has been proposed is highly complex, with a lot of floating point operations and parameters. That's definitely something that's not being executable in real time, that doesn't serve a constraint of power efficiency and things like that, right? If we try to make that work, would work, but it helps us at least to define the framework and leave headroom for implementation, I would say. So at least that's my thinking. I'm not sure, Francesco, what's your take on power efficiency in this case?
Let me know. I'm on your line. So as of now, 3GPP has been mostly studying how, whether there is a performance gain. And this performance gain isn't necessarily, or at least from their perspective, is not directly related to power efficiency, but it's more related to, can I have better beamforming in the downlink, for instance. This work so far is mostly done in MATLAB, and so, for instance, what we have done with the CMX is nice from a certain perspective because it executed on a real device. So definitely, if we want to go into reality, we need to consider more closely power consumption. And definitely we think, well, we believe that at least in the short term, the models that will be used will be probably more on the light side around from the study that is in 3GPP, so that will not be too complex out of hardware constraints. We definitely don't exclude that, with hardware advancement like, say, GPU or this kind of hardware acceleration, and possibly there will be a certain degree of power efficiency. Also, admittedly, these models are in general more complex than what a classic 3GPP codebooks so far require. On the other hand, the advantages that this brings seem better in terms of better beamforming, better throughput, is also a kind of revenue or justifies a certain cost, operational expenditure for the network operators.
Thank you both for that. And I'm aware that we could talk a lot longer, but unfortunately we're coming up to time. So I'd like to thank Francesco, Andreas, and most of all you, the audience, for being with us today. Once again, if you have feedback or ideas that you'd like to share, please do let me know. If you've got other questions and comments for Andreas and Francesco, I'll pass them on as well. Hopefully get back to you. But yeah, I'll hope to hear from you soon. And with that, thank you all and goodbye for now.